So what I want to do is start my presentation by sharing more into our program, our strategy, our mission, really our vision for quantum computing at Microsoft. So I'll roll the first video.
The Microsoft Quantum program is a global scale program focused on enabling commercial scale quantum computation. It's really about bringing quantum impact to people today and tomorrow.
Quantum computing has the opportunity to make an impact on the world right now in a revolutionary, game-changing way.
We're focused on developing every element of the quantum system, an end-to-end full-stack technology from the algorithms to the software stack to the hardware itself. To reach a commercial scale quantum computer, it requires revolutionary discoveries across physics, computer science, mathematics, materials science,
all of which have to come together to make topological qubits and multi-topological qubit systems. We have a team that's spread across 8 labs around the world. Although we're spread out, we are one team working towards one goal.
Building a quantum computer is a huge task. It's all the way from the software all the way down to where we control the quantum states that makes up the qubits.
Here in the lab, we have fabrication technologies, nanotechnology that allows us to turn dumb materials into smart devices.
The Microsoft Quantum program allows us to dream big. We need to dream big.
Azure is the world's computer. You have access to the tools, services, and solutions in a very familiar environment. And with Azure Quantum, we're bringing quantum solutions forward to that environment. We're bringing quantum impact to your fingertips. We're working with enterprises and companies around the world, energy optimization, risk and financial analysis in medical diagnostics, to identify where quantum solutions will bring about impact for their businesses. A great example is Case Western Reserve University.
We're working with Azure Quantum to optimize the way that people get MRI scans. Patients have access to faster and better MRI scans in a way that wasn't possible before.
We can make those scans up to 3 times faster by using quantum solutions on classical hardware today.
The really high-level scientific goal is to be able to solve problems that we can't solve today.
Azure Quantum enables every developer, every person, every enterprise to really tap in and succeed in their businesses and their endeavors with quantum solutions. And that's incredibly powerful.
Azure is the world's computer. What does that mean? Well, more than 95% of the Fortune 500 companies now use Azure, running their business on Azure. And we're adding more than 10,000 new customers every week. 40% of these new users are small companies and startups. Azure is future ready. It's built on a heterogeneous compute fabric, and quantum is the extension to that. In addition to operating hybrid clouds as we know them classically, we're also offering this will be a hybrid solution with quantum, classical hybrid solutions. And it's built on your terms. You can use the operating systems, the software, the solutions that you want. You can spin up a Linux VM, a Windows VM. All of these solutions sit side by side so that you have that choice. And you have the trust. Microsoft runs on trust. And you have that trust with the global scale, putting your business in Azure. But with all of the compute power that we have in Azure, 54 regions around the world, it's still, for the toughest compute challenges, not enough. So solving these grand challenge problems in climate and security, global food production, and many others requires more compute than we'll have in Azure. And so this is our mission for the Microsoft Quantum program. We're working to solve the world's most complex challenges by developing the world's most scalable quantum ecosystem. And we're doing this in a really open way, through Azure, in the way that Azure works. So Azure Quantum, which we announced about 3 weeks ago, is bringing quantum computing to Azure, to the world's computer. with the most diverse ecosystem of quantum hardware, software, and solutions. We're building off our foundations in the topological qubit and the work that we've done in software, applications, algorithms, and we're doing that with partners. So we're bringing partner hardware to this open ecosystem in Azure. And as with the rest of Azure, this is coming to you with world scale, and the scalability, the security, the reliability of Azure. And through quantum-inspired solutions, we're having quantum impact today using these quantum techniques that run already on the classical compute power that we have in Azure. And so I'll be talking about that more over this talk, and also Helmut Katzgraber will be talking more about that tomorrow. And so for us to realize as a community the promise of quantum computing, we need a full end-to-end stack that's integrated with a global cloud. So we bring Azure Quantum. It builds upon the work that we've been doing in the hardware space over the past almost 20 years, and the work that we've been doing in software tools and services and applications. So at the foundation of this stack is the quantum hardware. So this is our topological qubits in that effort, together with partner hardware. So we're thrilled to have IonQ and Honeywell joining us with trapped ion systems, superconducting qubits from QCI. This is a hybrid architecture, so classical hardware is incredibly important. So we're building a new advanced classical control systems together in Azure. We're building on this with the Q# and the QDK. So Q# is our quantum native language and the quantum development kit. And we're partnered with partners like 1QBit, bringing quantum solutions and quantum-inspired solutions to Azure Quantum through the quantum development kit. The QDK ships with a suite of simulators, a resource estimator, so we're bringing a really solid and diverse set of tools for developers to make it easy to get started on your quantum journey. And then, of course, the real impact is going to come from these applications and these areas that we know about today around solving hard optimization problems, machine learning, simulating physical systems that are inherently quantum in nature, and solving problems in cryptography. All in one place, integrated in Azure in a familiar environment. So I'm going to talk a little bit about our topological effort. So as we looked at the promise of quantum computing, of course, at the heart of these systems are qubits, the fundamental building blocks. We've made a lot of qubits at Microsoft, and we've done a lot of work on algorithms. This emerging field of quantum software engineering, and really getting deep into these algorithms, understanding at a really detailed level what's going to be required to realize some of these grand challenge problems, problems like climate and global food production. And that's given us a really deep understanding of what's required from the underlying physical hardware. And that's why we're asking more from our qubits. And so the hardware that we're developing at Microsoft is built on these topological qubits. And so the way to think about these qubits is like taking a knot in a rope. And so if you were to look at this rope and to look at it at a really small scale, it's impossible to tell as you're going along this rope whether or not the rope is knotted, in a true knot or not. And the way to think about it is that the knot is our qubit, and local noise coming in to probe the system is my little magnifying glass. And so with this topological qubit, we can encode the information in a much more robust way, lower the error rate, and that gets us to a scalable system that can solve these real problems. And building on that, so we need revolutionary work at the fundamental qubit level, and going up the stack kind of one little step further. These qubits need really precise, careful control and measurement. And so one of the exciting news that we're excited to share is our quantum lab in Sydney, Australia, has had a breakthrough on the classical control side of this problem. And the team has developed a chip that helps us with this scalability problem of getting to a point where we can scale to hundreds and thousands of qubits. But controlling these qubits without adding noise from the environment is a tough engineering challenge. We need to go from room temperature all the way down to millikelvin temperature. And this chip operates at millikelvin temperature. It's thermally isolated from the qubits and can scale to control up to 50,000 qubits with only 3 wires. And so we're investing in every single layer of the stack, and we continue to make advancements. We have the chip here in our booth. I invite you to come see it. And we just published a paper out on the archive if you're interested in learning more. So now I want to dig a little bit more into Q# and the Quantum Development Kit. Q# is our quantum native programming language. It's designed from the ground up for programming quantum computers. And we've really made an effort to use it. It's really an abstraction layer that abstracts away the underlying quantum hardware. And the reason for this is really simple. I'm guessing that not many people in this room are coding up your classical workloads using assembler-type languages and thinking about individual transistors. And for us to scale with quantum software engineering and solving these interesting problems, quantum's got to be the same. So we want to abstract away from that hardware and give a higher level language that makes use of libraries and abstraction layers so that you can continue to develop robust, durable code and have the hardware evolve. Continue to evolve, and so that your code can be robust for that. Q# comes with a range of simulators, and now with Azure Quantum, a range of execution environments. It comes with a rich set of libraries. We've done a chemistry package that integrates with a leading chemistry modeling tool by Pacific Northwest National Lab, and a set of katas, so learning modules, so you can get started on your quantum journey. And we also have a no-download execution environment, so you can just go to our website and start developing code just in the browser without installing anything. And so 2 years ago at this conference, I demoed Q# for the first time. It was a week before we launched the code, and we actually hadn't released the name of the language yet. And so I was thinking about this moment 2 years later, and I thought it'd be really fun to do another demo of Q#, this time running on real quantum hardware, which is, I know, something that a lot of you are eager and excited to do. So actually, before I switch over to the laptop, I'll set this up a little bit. So the problem I'm going to demo is this hidden shift problem. And so this is a quantum algorithm for determining the shift between two functions. And so this is one of these fundamental building blocks in quantum programming. And so I've illustrated that with these 2 circles up here. So these are shifted by 3. It's obviously easy for us to have a look at that and see that. So we know this answer going in. It's a simple answer. But in a real problem where you didn't know the answer ahead of time, this has an exponential number of solutions. So this is an exciting algorithm because it has a known quantum speedup. And so this is the algorithm that I'm going to demo. And I'll shift over now to the laptop, to the demo machine. OK, so what you see here is I've got Visual Studio open. And so we talked about this. Quantum will be a hybrid architecture. And our whole system is architected in this hybrid way. And so I've got a couple files open here. This is my C# code, and this is where I'm going to call the quantum algorithm and set up the file. And then I've got this Q# code over here with the hidden shift. So I'm not going to go into a ton of detail here on the quantum algorithm and how that works, but I wanted to point out a couple of things just to demonstrate this idea that this high-level programming environment. So we're bringing libraries in. So you'll see in this function, one of the fundamental pieces of a quantum algorithm is putting the qubits into superposition. So doing this Hadamard gate to have an equal superposition. And this line right here shows an example of using that in a functional way. So this is apply to each, and it's applying a Hadamard gate to every single qubit in the register. And so rather than having the programmer have to program that for each and every qubit and having that be fixed to a set of qubits and hard-coded in, this function just can apply a Hadamard to every qubit in the register, which is kind of arbitrarily sized. The CA in that line means that it's controllable and adjoinable. And so this is taken care of for you automatically. You don't have to create the control and the adjoint for this, and the code takes care of that for you automatically. And so this is the way we're going to program quantum computers, of going to these higher and higher levels of abstraction. And so I probably should have run this before I started talking, but this is where we are. So I'm going to run this from the C# code. This sometimes goes a little bit slow depending on the network connection. But we'll see it start up in a second. You can see it working in the background. And so I'll talk a little bit about this. So now in this first demo, I'm running this through Azure Quantum. So this is using an online simulator. So it's calling our Azure Quantum service. So I see it started up now. I'm going to run this 1,024 times on the online simulator. And so the online simulator, these are, hopefully everyone can see that's a little small. The online simulator is running with perfect qubits. Let's make this bigger. And so you can see I measured this shift of 3 when we ran it 1,024 times. I got that answer 3 back every single time. And so typically we run quantum algorithms many times because these are probabilistic systems. But with perfect qubits, I get that answer back every time. OK. I'm going to close this window. So now I'm going to go back, and so this hidden shift, the Q# code, is going to stay the same. And I'm just going to change one line of code in the C# code. And so instead of having the online simulator, now I'm going to type in IonQ. And so IonQ is one of our terrific partners in Azure Quantum. And so now, instead of running this in the online simulator, I'm going to run this through Azure Quantum down to the IonQ hardware. And as you'll notice, just changing one line of C# code, no change to the quantum code, Q# code. So I'll click Run again. OK, so we already got our results back. And now you'll see a little bit different results here. So this real quantum hardware has an error rate. And so now I'm getting this full distribution. Instead of getting the same answer every time, I'm getting a distribution of results. And so now you'll see we did get the answer 3, thankfully. And we got it the vast majority of times. 782 times we got 3. But now you'll see we're getting a distribution of results because we have that error rate in the physical hardware. OK, so that's my demo. I'll switch back to the slides. OK, I'm going to cover one last application area in this talk and shift gears a little bit from quantum algorithms and quantum hardware into the work that we've been doing in quantum-inspired optimization. And so this is using quantum techniques but running on classical hardware. And so if you think about solving a really hard optimization problem, what we're trying to do is minimize some cost function. So I have an example cost function here. And of course, this is a very simple cost function that everyone in the room, I think, can find the minima of. But this can become really, really complicated with real-world problems. And so where you have hundreds of thousands of variables, they can all be interacting heavily. And this becomes an exponentially vast search space. So when we solve these problems classically, a typical technique is something like simulated annealing, where you can introduce a thermal jump. But when these cost functions are really rough, when these have these tall, narrow barriers, that makes it really difficult for these classical systems to find those global optima, and you tend to get to locally optimize. But quantum systems quantum particles can tunnel out of these local optima and find much better solutions much more quickly. I'm not going to go into a ton of detail in this today, because Helmut's going to talk more about this tomorrow, and I have another slide about when his talk is, about really showing this pattern matching of what are the good problems and solutions for this quantum-inspired optimization. But where it gets really, really interesting, so you can have, for a fixed solution quality, you can find the solution faster, or vice versa. But when it becomes really interesting, when I'm out talking to enterprise customers, is you can have much more complex systems where you're making fewer assumptions and fewer simplifications. That's where it becomes really powerful. And we're out talking to customers every single day. We've got terrific customers and partners working with us on these problems. And they show up all over the place. And Helmut will go into this more tomorrow, but everything from verification and validation, signal processing, materials discovery, job shop scheduling, and I'll just highlight the last one, traffic, car sharing, logistics. So come learn more about quantum solutions tomorrow, with Helmut, tomorrow morning. And to close, I wanted to share an example of a customer that we're working with. So yesterday we announced, and you heard about it in Ben and Elisa's talk yesterday, the work that we're doing with Ford on traffic optimization. And so this is a problem that I know everyone in this room is intimately familiar with. I know my ride to the airport yesterday was excruciating. And think about, as we bring these solutions for big compute challenges, we're dealing with the now, which is, traffic lights and metered ramps to control the traffic. But in the future, you can imagine the types of solutions if we were able to develop an optimal route for every car on the road. This could be a really different reality for us as we commute to work and commute to conferences. And so, we've been working on a wonderful solution to this with Ford. The solution is really based on grouping vehicles having nearby waypoints and choosing the optimal routes for each of these cars. And because these quantum solutions run on scalable hardware that's already deployed in Azure, and we have this heterogeneous compute fabric in Azure with CPUs at scale, GPUs, FPGAs, we can really tune these solutions to these problems. We do this with customers and partners every day through our Quantum Early Access program, and subject matter experts from those companies come in and work directly with our team of quantum algorithm developers to develop custom solutions on top of what we're building in Azure Quantum. And we're seeing some really exciting results from that. You heard a little bit about the Case Western Reserve University work. Satya Nadella shared that in his keynote at Ignite. And I wanted to share a new video with you highlighting the work that we're doing together with Ford.
Automotive is changing now. People aren't just buying cars for getting from point A to point B. Experience is much more important.
Right now, every car is a moving computer. A huge amount of computations are being performed in vehicle or via the cloud. At Ford Motor Company, we have the vision in terms of what can drive the future of not only the automotive, but also the future of computing.
Quantum's really promising for how it can solve problems that haven't been traditionally solved before. We are looking at ways now that we can take some of the concepts from quantum and apply them to problems we have today. Ford brings the expertise from the problem areas and where the value really is for us. Microsoft brings the quantum expertise and the team together to help formulate the solution.
One of the use cases that we explored is a congestion mitigation problem, where you have a bunch of cars requesting for routes at the same time and planning to share the same route segment in a city. Under the current technology, what happens is there's a selfish routing algorithm that works, where you actually assign routes to each of the vehicles so that they can optimize their travel time without even being worried about how many cars are planning to share the same route segments, which actually creates a congestion.
What we've seen with bringing quantum-inspired optimization to the traffic optimization problem is we can solve these problems in some cases orders of magnitude faster than can be done with conventional computing. And that could really have an impact on people's everyday lives.
It will help reduce congestion in cities where congestion is a big problem. At the same time, it will help individual drivers to improve their commute times, especially in the rush hour.
We're just scratching the surface with looking at traffic optimization. We see opportunities across the spectrum in automotive, everything from traffic, thinking about mobility as a service, thinking about optimizations within manufacturing and supply chain, to things like design of better materials and new types of batteries. The possibilities really are endless.
The automotive industry is unique in that it's got really high volumes and it touches people every day. So even changing small things for the better make huge impacts both to our business as well as to our customers. We're trying to add value to people's lives, but at the same time make the world a better place. As cities get larger, as the environment changes, any little bit we can do really helps.
And I'll close there. I hope you'll join us on this quantum journey. We're excited to bring this technology to Azure. We're excited to be working with companies and partners like those of you in the audience. So I hope you sign up to learn more about Azure Quantum, become an early adopter. We'll be making this available in private preview to a small set of folks first over the next coming months. Try out the Quantum Development Kit. Like I said earlier, you don't have to install anything. You can go to our tools on the website and start coding right in the browser. And join the Microsoft Quantum Network. We're working with a terrific group of academic institutions, startups, partners, and enterprise customers, and we'd love to have you join us. Thank you. Do we have a couple minutes for questions? Anyone brave? There's one over there. Great.
Hi, thanks for the nice talk. I was wondering if you could maybe elaborate a little bit more on the state of the topological qubit that you're working on.
Yeah, so we don't have any news to share, but we've, like you said in the talk, we've made lots of qubits at Microsoft. This was a program that we started almost 20 years ago with this idea of building qubits out of these Majorana particles. And so these were first observed experimentally in our lab in 2012. And we've made tremendous advancements on kind of all aspects of developing the topological qubit, not just making one, but actually making these in a scalable way. So we have significant research and work on materials development, manufacturability to make these nanowires and to be able to wire them up and form qubits. We've been making Majorana particles. These are heterostructures. We make nanowires, and they're superconducting, semiconducting nanowires as heterostructures, and these Majorana particles show up at the ends. And so we've been making these robustly for years, and we're excited. We still feel really good about the advancements that we've been making on the hardware side. And like I said in the talk, with Azure Quantum, we will bring these topological qubits to Azure, and they'll sit right alongside. I see some of our partners right here in the front row. So they'll sit right alongside our partners in hardware, and really bringing you that choice and selection, just the way that the rest of Azure works. So thank you.